We'll continue on the classical, the reliability theory, which is pretty the basic theory to capture the concept with the 100% understanding. Then, of course, we will expand into the multiple dimensional space. Then sometime near future, or if you really like wants to have a file which explains the first order and second order approach, of course I'm willing. So I don't want to just dump it to you. As I give a lecture, then I give you a handout. Another section, I'm giving you another handout. I'm also preparing on the way, and so on. So target week for to show you how to handle the multi-dimensional structure reliability analysis. Gonna be around the end of the October. So then all the complicated problem sets are on the way, but as long as you understand the concept clearly, then you can handle very nicely as a bi-weekly project or term project or whatsoever. Okay, so that's the way I'm going to do. Still, the Wednesday, I give you a brief and a quick overview on the processing reliability a little bit, expressed as time to failure. Another one is really structure reliability, push around the structure reliability, what that is, using the weakest link problem. And I'm going to go back to the time to failure concept and giving you a little bit more on that. Then we'll jump into the structure reliability. Then we must capture the essence and the concept of it. Okay, that's what we're going to do. All right, so continuations. Classical. Classical reliability analysis. Expressed as reliability, RT is the probability, P or PROB probability, such that T is T. What's this? Higher or lower or below, which is the time to failure. This is a time to failure. Is for the reliability is higher. Okay, it's higher to the specific time t, and if it's lower, less than the specific time t, then that's really the probability of the failure, but measured as the time to failure, which is equal to 1 minus, we have done this Wednesday, FT. What's FT? 성태, what's the FT? Of what? Of course, this is a probability such that t is less than or equal. So I'm going to just use one side only to cover them all, because PF plus S is equal to 1, that concept. So probability such that the time to failure is less than or equal to t is what the FT is. And this is back to this one. And as I give you another expression, I give you also RT, t is equal to 1 minus 0 to t is FTT. This is integration parameter, d tau, or this is equal to t to infinity ft tau. I give you this the Wednesday. And the probability model, typical probability model, I mentioned to you already, which is FT, typical model, and 1 minus EXP minus T over beta alpha. T is 0. So this is how many parameters do you have to determine to fit your data? 2 parameters, alpha and beta. So if you look at this is a typical of Weibull distribution, 2 parameter Weibull distribution. So you can test out by varying the alpha and beta. But if you look at my note, the previous set of note, then I give you also the probability curve for different alpha and beta. And RT, so this is Weibull. So first clue is you have to get the model, probability model. If you don't have a probability model, then you can evaluate the reliability or time to failure, the vice versa. So that's the first set to really get that. And which is 1 minus FT t, so which is equal to using this EXP alpha. Of course, x is larger than or equal to 0. Okay. survival. And next one is exponential. Of course, exponential model is one parameter model. You can specialize from y-ball by setting the alpha is equal to the 1. And usual parameter you handle for time to failure. Time to failure is of course a random variable, is expected value or mean value. The E of t, which is equal to first moment, tau ft, tau d tau, from 0 to infinity. Again, model you have to get. Then you can get the first moment. Then first moment is a mean or expected value of time to failure. So then you can compute. Sometimes you have to deal with the failure rate or failure rate function. So to get that, this is probability of failure. If you have a probability failure, then you can deal with probability of the survival. So it's a complement each other, so you can of course compute that. So probability of the failure within given time, let's say t and t plus delta t between, okay? So to compute the probability such that t is between t plus the delta t. So now this is a random variable. Then you've got to get the probability density function of the t. Then of course I can say, okay, so here is the probability density function. I'm going to say this is from t to t plus delta t. So probability is concerned is nothing but area for that interval. So what you can do is, this is of course a probability of the failure is equal to f t plus delta t. What that is, area up to here. And you can subtract now area up to here, then to get the probability of the failure in between. Right? So I'm going to take away f t. Then this, if you carry this out in terms of the minus 1 minus RT t plus delta t, then which is minus 1 minus what? R t t. Then you can cancel, this guy cancels up. Then you can have expression this is sort of the approach for time to failure computation area, processing probability, which I'm not going to carry all the way, because giving you a little bit on this side, then I'm going to jump into the structure reliability, okay? But some information on the other side of the wall. And then in the processing probability or reliability, you deal with the failure rate, let's say, function. So failure rate function, like a bathtub curve. Last Wednesday I introduced a bathtub curve. This bathtub curve is really failure rate, and you can deal with the normalized failure rate per unit time. That's what the failure rate function. Failure rate function is equal, usually called ZT, is RT minus RT plus delta T normalized by RT tau per unit time T. Okay. So it's called, as I indicate there, the failure rate function. And as you see in page 4, the bathtub curve comes like this, which is T, and this is exactly ZT is what the people draw as exponential decay function for the time to failure, things like that. And that's about all I'm going to cover, okay? And a typical model, in page 5, again, I introduced the two functions. One is a Weibull function, another one is exponential function. So this is Weibull. Another function is exponential function. Two model is a typical, and you may have also other model for time to failure, okay? But in the class, when you do some little project, so this two function is what I'm going to deal with to see the concept. So this is exponential, the Weibull function is right out there. And for the exponential function, very close to the Weibull function, and which is 1 minus ft. T is equal to e to the minus t over zeta alpha. By the way, I think I made a mistake. Not the mistake, but this alpha, some author used as a 1 over theta. But, 1 over theta is equal to alpha. So don't confuse. Some paper, they use alpha. Some paper, they use like 1 over theta. But is inverse each other, so there is no reason to confuse it. So this is I converted into the same format, looks like. So I think the same alpha is what I'm using. So that's what that is. And here, to get that exponential, this is reliability, the term. But for the in terms of the probability of failure t, this is equal to 1 minus e to the minus t over theta. So take a look at my notes. My note is pretty thorough. So to get the reliability model, you have to take away ft, then you will have that model. Nothing to confuse. So as we have done this expected time to failure, there is another term that processing the reliability analysis using it is another term, MTTF. MTTF is mean time to failure. So ET, exactly that, mean time to failure. So this is equal to the exactly that ET, and they have a specific name. Mean time to failure. Jungan, have you heard the MTTF, right? Mean time to failure, processing reliability, okay? So I just introduce a few terminology and really basic equation for the processing reliability analysis. And this MTTF for exponential model, so MTTF for exponential model is equal to theta. You have to take the mean. So mean happen to be the theta. And mean time to failure for Weibull distribution is equal to theta gamma 1 plus 1 over alpha. Something mixing a little bit, but you can investigate. Look at my note. The other day, over the weekend, I tried to unify the notation written in this book or other book, but make sure check this that this is correct. Okay. Sorry to jump a little bit, but this should be correct. What my concern is in the Weibull, I did not, in this equation, I don't have alpha, but alpha, I mentioned that has a relation, okay? So check back these relations a little bit, would you? Check back, and I'll look back my note also. So Please check back. Okay, for time to failure concept is concerned, this is all I'm going to do. Okay, so we push around the structure reliability, then what's in other side of the fence, and this is what the basic idea and concept is. So mean time to failure, very important parameters, and time to failure computation is very important. It's totally different from structure reliability in a sense. Like electric circuit has a failure, then idea is really to predict the time to failure. And lots of equipments has the same kind of the electric circuits, same kind of the motors, many of them. And as I mentioned, motors like a 600 per ship, frigate or destroyer class ship, and electric valve, so many in there, then their concern is time to failure. But for structure, the reliability is concerned, or structure failure is concerned, the probability of the failure has to be very small. It's something like 10 to the minus 6, 10 to the minus 7. So because one failure give a total disaster, that's a quite different concept. So one of the difficulty to compute the structure reliability is stability in the computation, because you are looking for really very small the volume in 3D space to get such a low probability of the failure. So it's a different concept, but this is like a time to failure concept for the lots of the component and the system, rather smaller system in the equipment, okay? All right, so now back to structure reliability. That's what I want to pursue from now on. That's what we're going to do. And I started with the probability of the failure. I started probability of the failure is a probability such that resistance is less than equal to S. S is a loading. Sometimes I use a P, but it's the same thing. Or I can write this as a probability such that R minus S is less than equal to 0, or slowly evolved, or this is equal to the probability such that function g of, let's say, x, many random variable x in general is less than equal to 0, and then I give you Wednesday like this equation. This is equal to FR x f s x dx without proof. Wait until around page 11. And this to be equal, there is a condition such that R and S are independent. Okay. It just goes up and down. And if I write one more line, it's all different expression, but it's all identical. This is f p f x dx. So this can be f p f, okay? For the two random variable, like R and S, everything is visible. So we're going to spend some time for next few weeks to really taste inside what's happening. So then when you jump into the multidimensional, then it makes sense, okay? And so we're going to look at the special case here. Special case. Special case 1. I can do easy case here, then you can do a little bit more complicated at home. Both special case, both R and S follows normal distribution. You have to develop the probability model. Without knowing the probability model, you can't just solve. So assume R and S follow the normal distribution function. We learned the normal distribution function. It's very easy to handle. And I'm gonna let's say R minus S. I'm gonna call this as M. Very typical notation for M. M is called the safety margin. If R and S follows the normal distribution, then M is concerned what probability model this safety margin will follow. Normal distribution. So that's why it is very easy. And here mu M is concerned mu R minus mu S. We have done all this, right? And sigma M square, what's the sigma M square? Variance of M, or the square of standard deviation of M, is equal to sigma R square plus sigma S squared. For normal distribution case, special case, then probability of the failure can be defined as a probability such that m is less than equal to 0. Can I do that? M is equal to R minus S. I can do that. And this is equal to, of course, M follows the normal distribution is equal to the minus infinity to 0 f m m. How can we keep going up? Integration of what? This is m, this is fm. Integration up to the 0 point is what the probability of the failure. And we know the normal distribution, and the normal distribution is concerned is again minus infinity to 0, and this is 1, and sigma m square root of 2 pi e to the minus m minus mu m square to sigma m square and dm. I just plug in the normal density functions in there. So we know the standard deviation of safety margin. We know the mean of safety margin. And as we have done before, I can reset, let's say z is equal to m minus mu m sigma m, you remember? Then take a derivative like d z over dm, then this is gonna be mu m sigma m. Then you plug in, express, then dm is equal to what? Minus mu m sigma m. Try to normalize it, right? Then change into the standard format for normal distributions. So plug in all this into here. Plug in these guys all in there. Then you can have a really nice form, minus infinity to this guy. Of course, you can set this as 0 is there. If I write this is minus mu m sigma m and 1 over 2 pi e to the minus 2m dm, then I can rewrite this guy as standard normal distribution function 0 minus mu m sigma m equal. So over here, sigma over here, the sigma m x is equal to minus infinity to x and the square root of 2 pi and 1 e to the minus 2 z squared. Have you seen this before? And this is arrow function. And I give you also table, right? Normal distribution table. Here is a good thing. Here is mean is equal to 0. And standard deviation is equal to 1, right? So you can look up the table, or in the MATLAB, you know, they already computed. And if you ask what the value, just the print out. So anyway, this is what the standard form of normal distribution. So standard form. So standard form really means it's like this. So mean is equal to 0. Then it has a standard deviation. It's up to the x area up to that point. But we know half of the area up to here is what value? Up to the 0, half of the area is half, 0.5, right? So another half is 0.5. So if you look at the table, it only dealing with the half, because the other half is already half. So if you say, I want to compute up to here, this point, x1, then you have to compute the area up to here. Up to here is a half. All you have to concern is that area, or some table provide the area up to here, the complement side. Then what happened? To get area up to here, you have to subtract the value shown in the table, subtract from half to get this area. 성태, it's simple, right? Yeah.
I think that one is wrong.
Oh, it's wrong? Okay. Let me see. So, it's a substitution. It's m minus mu m over sigma m. And take a derivative, right? Oh, this is equal to this, right? It should be 1 minus. Oh, this should be plus. Thanks. 잠깐만 보자. m minus mu m. So you should take a dm. That should be is 1 over sigma m. So now m is equal to, right? M is equal to sigma m. Is it? What else?
over equivalent time at the end. Sorry.
Why don't you come out fix?
저 대입한 치환을 쥐도 치환하는.
어떤 거? 예술이 나와봐. 그래, 해봐. 그래, 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 맞아. Thank you. That's it. That's a integration parameter. Okay? So, anything else? It's good? And if you look at the standard normal distribution function, which I gave you the handout a couple of weeks ago, I want you to review that. What I found out was this is really error function. But believe it or not, this was missing in there. So please take a look at it. This is corrective form. So, okay? All right. So for the normal distribution situation, is somewhat easier. But for other distribution, not easy. Even if the two parameters R and S. So Monday next week, I do the normal distribution. Then I want you to do the other case, which I'm going to set up over the weekend. Then I'll assign Monday, because after Monday you have nothing else to do. So I'll assign the one good size homework problem. But this time I'll assign the probability model for resistance and load S. Then you can really manipulate and look into insight. Okay, it could be a log normal distribution, or could it be exponential distribution, vice versa. So continuation for this is PF. This is the goal. This is the goal, to compute that. Then you can compute the structural reliability factor. So here is equal to, you know now the phi m and minus mu m over sigma m. Right here. So it's a continuation up to here, which is sigma m, which is minus and this term mu m over sigma m has a special meaning. Let's call the beta. This beta is called the reliability index. This reliability index, if you look at the carefully, carefully, the inverse of the reliability index, beta is equal to what? What's the sigma m over mu m? What's the usual value of sigma over the mu. 1령. I'm glad you really wake up this morning. This is called coefficient of the variation. And this reliability index plays a very important role in the structure reliability. And this was first used by Alan Cornell in 1974. He was a professor at the Stanford University. Then he disappeared. He was very strong in structural reliability. I didn't pursue where he was since then. He received his PhD from Cornell University but disappeared. I have never seen his paper since then. So it's Alan Cornell. In 74, he was very young, around the 30s. I don't know what happened to him. Okay, this is a beta, so I can rewrite this guy as phi m minus beta reliability index. Since then, many authors in this area used beta as some sort of the measure. So if you look at, if I just draw again, this is like mu m. So this is f m, and this guy is m. If I call this, so sigma m times beta is equal to the mu m. So here, up to here, this guy is sigma m times beta. Of course, sigma m is a dispersion, measure of dispersion of density function. And it has such, it's not the big things, but can be a measure of shift of probability density function. Okay? We'll continue next Monday. So for normal distribution situation, as you see, very elegant. And after I assign you next Monday one problem set that you could deal with the possibly log normal distribution and the normal distribution, then I want you to conduct the analysis, and I'm going to give you some realistic numerical input, then you can also get the result and find out what that really means in terms of the structural reliability. Okay, today is a Friday, so have a nice weekend. We'll come back Monday morning. Okay, that's all today.